Welcome back, everyone. In this lecture, we will continue with elementary number theory. So, in the last class, we saw the division algorithm, and then how one actually writes a GCD of given integers to integral combination of those integers. So now we will actually define some more elementary properties of these numbers. For example, we will start with relatively prime numbers. So we call two integers, they are relative prime if the GCD of AB is 1. Okay. So here is the definition. So let A comma B being in Z such that so AB not both of them are 0. Okay. So then we say A and B are relatively primes if the GCD of AB is 1. And then this definition you can actually generalize to any given finitely many integers, not all of them 0. So if the GCD of those numbers are 1. Okay. So you can also talk about relatively primes in pairs or pairwise relatively primes. Okay. So if you start with integers a1 etc. an, we say this is actually pairwise relatively prime if you take any two of them, they are relatively prime. The GCD of AIAJ is 1 for all I not equal to j. So this also can be called relatively prime in pairs. Okay. So suppose GCD of A comma B, it is being 1. So this can be expressed by saying that A and B are co-prime. Okay, or A is prime to B. So all these terminologies are used in the literature. So now let us start with A and B being co-prime integers. That means GCD of A comma B is 1. Okay, so here is a small lemma, and it is very important lemma in order to prove, for example, prime factorization is unique. We use this lemma. Okay, so you start with A comma B in integers such that the GCD of A comma B is 1. Suppose this A divides BC for some C integer. So then what we can conclude immediately that A should divide C. Okay. So because the GCD of A comma being 1, so they will not have any common divisors. So that is why if A divides BC should force that A divides C. So how one proves this? So recall that GCD of A comma B can be written as integral linear combination of A and B. So in particularly we can write 1 as some AX plus BY for some x comma y inside integers. Okay. So now if you multiply by C on both sides, you get C equal to ACX plus BCY. So now note that A divides A. So A divides A will imply A divides ACX. So now what is given? So given is A divides BC. Since A divides BC, so A divides BC will imply A divides BCY. So now if you put them together, so this plus this will give you A divides ACX plus BCY. So what is it? ACX plus BCY is exactly C. So which is what we want. Okay. So if AB are co-prime, if A divides BC, then that must imply A divides C. So this is called Euclid's lemma. So this also has a name in the literature. So Euclid's lemma. Okay. So, now as a corollary you can also prove the following. If A and B are co-prime, okay, as before. So, GCD of A comma B is being 1, and let us say A divides C and B divides C. Okay. So, then what one can conclude? One can conclude that AB must divide C. Okay. So, I will leave it as exercise to check this. So, this is not that hard to check. Okay. So, once we have this greatest common divisor, so that also motivates us to define what is called least common multiple. Okay. So, here is the definition of least common multiple. So, which is denoted as LCM. So, what is LCM? Least common multiple. Okay. What it is? So, again start with two non-zero integers. So, let A B, both are non-zero integers. We are going to talk about common multiple of A B. So, better A B be non-zero. So, then the least common multiple, which is denoted by LCM of A comma B. So, this should satisfy two properties. First of all, it must be common multiple. So, that means A should divide this and B also should divide this. So, that means LCM of AB must be common multiple, and it is the least positive integer, that is multiple of this. So, that means A divides L and B divides L. Okay. So, this LCM first of all is non-negative integer. Okay. And if L is non-negative, then that would imply that L is greater than or equal to LCM of A comma B. So, this is the least positive integer such that A divides L and B divides L. So, now it is not hard to prove that there is a very close relationship between LCM and GCD. So, that is actually given in the next lemma. So, what is this? The GCD of AB. Okay. So, if you take AB are two non-zero integers, then the GCD of AB times LCM of AB must be exactly equal to the modulus of AB. Of course, this is something you can assume from the beginning, AB being positive integers, then it is just AB. Okay. So, this is again very easy to prove. So, for example, what one can try to prove, you take either mod AB divided by LCM of AB and then show that is the GCD, or you take mod AB divided by LCM of AB and then try to show that is the GCD. Okay. So, this is something I will leave it as exercise to check. And here is another important property. So, if you take LCM of multiples, okay, if you take LCM of some multiple of A and then multiple of B, then you get exactly the mod M times LCM of AB. So, because LCM is again being non-negative integer, so you get this. So, this is true for all M in agent. So, these are all some elementary properties that actually comes very often. Okay. So, now so with this we will actually conclude the divisibility. So, now what we do, we actually start with this congruences. So, this is something I introduced using the cosets A plus B z. Okay. Maybe I will actually start with equivalence relations, and then using that we will actually see what congruence means. Okay. So, let us first start with the definition of congruences, and then maybe this is one of the very first example that you see as equivalence relation. So, maybe we will actually see the properties of this congruence classes, and then from there we will generalize this equivalence relation. Okay. So, what is congruence actually? So, again congruence that you talk about modulo M. So, it is arithmetic modulo M. So, you start with some M being non-zero integer, or you can safely assume to be positive integer, there is no harm. So what is the definition? So you fix m, which is a natural number. So you can take it to be non-zero integers, but still one can replace with minus m and then take it to be positive integer. There is no issue. So you take a b being two integers. Okay. So you want to say that a is congruent to b modulo m. Okay. So the notation wise a congruent to b modulo m. So this is the notation. So when you want to say a is being congruent to modulo m, so if and only if this m divides a minus b. Okay. So whenever this m divides a minus b, then you denote this a is being congruent to b modulo m. Okay. So basically if you think in terms of reminders, okay, so the remainder that you get by dividing, okay, a by m and b by m both should be same. Okay. So let's see. So you have a, so you divide by m, so you get q1 m plus some r1. So 0 less than or equal to r1 less than m, and then you divide by m, so you divide b by m, and then you get a remainder r2, which is again less than m. So then what happens? So if m divides a minus b, so then that would imply that immediately that m divides this q1 minus q2 times m plus r1 minus r2. Okay. So now you can see that this is already multiple of m. Okay. So that means, so you can rewrite this as q1 minus q2 times m plus r1 minus r2 equal to some q times m. So now since m divides the right hand side, m divides the first term in the sum. So that would imply that m must divide this r1 minus r2. But note that r1 and r2 both are actually less than m. So without loss of generality, you can assume r1 is greater than or equal to r2. In particularly r1 minus r2 will become greater than or equal to 0. So now r1 minus r2 is being non-negative integer, and clearly this is smaller than m. So that means it cannot be multiple of m unless it is 0. Okay. So that forces that this r1 is equal to r2. Okay. So from this condition, m divides a minus b precisely gives you that the remainder that you get by dividing a by m and by dividing b by m, they must be same. So that is what you are encoding as a is congruent to b modulo m. Okay. So since we don't need to really compute r1 and r2 to see this, we can say in terms of a and b. So we just take this as definition, m divides a minus b. Okay. Now what are all the properties this congruence or the congruence will satisfy? Okay. So the properties are elementary, I will leave it as exercise. So this is something I will leave it to you to check. So you start with, let's say, a, b, c, d integers. As before, you fix m in n. So now what happens? If a is congruent to b modulo m, again all these properties can be proved using the divisibility properties. Okay. So now a is congruent to b modulo m, that means m divides a minus b. Then that would immediately imply that m divides b minus a. So in particularly b is congruent to a modulo m. Okay. But before that, it is easy to see a is congruent to a modulo m. Okay. This is true for all a. So a is already fixed. So let's not worry about it. So this is called reflexive. Okay, reflexive property. So this is called symmetric property. So, now there is this transitive property, okay, the transitive. So, what transitive says, if A is congruent to B modulo M and B is congruent to C modulo M, so then that should imply A is congruent to C modulo M. Okay, so how you prove, for example, M divides A minus B and M divides B minus C. So, then you add them, you get A minus C. Okay. So, not only that, so this is all with respect to, so these are all properties of this relation, that is A congruent to B modulo M, that relation. So, it is reflexive, symmetric and transitive. So, on top of it, this congruence also well behaved with respect to other arithmetic operations. For example, you have addition and multiplication in your integers. So, we can also see how it is behaved with respect to them. So, then you can see that if A is congruent to B modulo M and C is congruent to D modulo M, so then you immediately get that A plus C is congruent to B plus D modulo M. Okay. And more generally, what one can do, one can actually take any combinations. Okay. More generally, you can take AX plus CY. So, sorry, A is congruent to B. So, AX plus CY is congruent to BX plus DY modulo A. So, you can add component wise. Okay. So, you get this. And then you can also multiply them. For example, AC will be congruent to BD modulo A. Okay. So, with respect to multiplication, with respect to addition, this congruence is actually well behaved. So, now it is not difficult to see if D divides M. Okay. So, then A congruent to B modulo M will imply A congruent to B modulo D. Okay. So, and A congruent to B modulo M. So, this will imply that A congruent to B modulo D. And similarly, you can also multiply, there is no issue. So, if A congruent to B modulo M and then C is non-zero, so then you can multiply AC congruent to BC modulo now MC. Okay, you can scale all of them. So, now, so all these properties are satisfied because integers you have addition, multiplication and so on. So, this congruence is actually well behaved with respect to. So, now what we are interested in, we are interested in complete residue system modulo M. Okay. So, we already seen that, for example, if you take this M which is a positive integer. Okay. So, then if you consider dividing each integer by M, so then you will be actually getting this residues. Okay. And then we have seen that these residues can be between 0 and M minus 1. So, but this also can be changed to 1 to M or 2 to M plus 1 and so on. Okay. There are many system of residues you can talk about. Okay. The standard ones. So, what is the meaning of that? The meaning is this Z can be partitioned into, for example, MZ union MZ plus 1 union MZ plus 2 and so on, union disjoint union MZ plus M minus 1. Okay. So, in particularly this 0, 1, 2 etc. plus M minus 1. So, this set has this unique property. So, what is this property? So, given any integer, okay. So, this is actually you can call it complete residue system modulo m. Why? Because given any integer y in z, okay, there exists exactly one x from this 0, 1, 2, etc. m minus 1 such that y is congruent to x modulo m. Okay. So, now if you think about it, this you can generalize to any x1 etc. xm. Okay. So, here is the definition. So, you take any m number of, because there should be at least m residues, okay, that is what we have seen. So, you take x1 etc. xm. So, these are all some subset of integers. So, this is called, okay, complete residue system modulo m if given any y inside z, there should exist xi such that y is congruent to xi modulo m. Okay. So, it should lie inside that. So, more theoretically you can see that. So, this is exercise. Z can be written as x1 plus mz, okay, and this is exactly 1. So, it is unique. So, this becomes disjoint x2 plus mz union etc. union xm plus mz. Okay. For example, so we take it as exercise. So, if you take 1 etc. m, so this is one complete system of residue CRS mod m. Similarly, you can also translate and then you take 2 to m plus 1. So, that is again another complete residue system. Okay. Like this you will be able to produce many of them. Okay. So, now we have some understanding of this congruence classes. Okay. So, let's prove actually really what it actually does to the set of integers. Okay. As I said before, so this congruence is indeed a relation that you define on integers and that satisfy reflexive, symmetric and transitive property. So, using this property you can prove that this set of integers can be divided into some smaller equivalence classes. Okay. So, those are all called congruence classes. So, first we will define what is the residue class or the congruence class, and then we will see like how one can get this decomposition. Okay. So, as before, fix this m which is a natural number, and then let a is an integer. Okay. So, we want to talk about this class A with respect to m. So, this is the residue class. Okay. So, this is the residue class or the congruence class, okay, modulo m. So, residue class of A modulo m. Okay. So, what it is? It is consisting of all those integers b such that b is congruent to A modulo m. So, basically what are you telling? You are telling that, so this is A m is nothing but, so those integers b such that when you divide by m, the remainder that you get from b and you get from A, they are all same. Okay. So, now if you think about it, this is same as saying you collect those integers z from other definition. So, b is being congruent to A modulo m will tell you that m must divide b minus A. So, now if m divides b minus A, then that would imply that b minus A can be written as some mq. So, then you can see that then b is nothing but mq plus A. So, now you can vary any q, still you will be getting those numbers. So, it is easy to see that mq plus A is inside the residue class m for all q is in z, and given any b inside this residue class should look like this. So, that forces that this residue class must be of the form this A plus m z, okay, or otherwise A plus q is in integers. Okay. So, now this is the residue class associated with A. So, here is the lemma, so which actually justifies, so why it actually partitions the integers. Okay. So, if you take two residue class, okay, one is associated with A and another one is with B. So, let A be inside integers and as before fix this m in n. Okay. So, then the only one of the following can happen. Okay. So, either we have the class with respect to m, the residue class of A with respect to m is equal to the residue class with respect to a residue class of B with respect to m, okay, or they are disjoint. The intersection will be empty. Okay. So, only one of the following happens, either they are equal or they are disjoint. So, how do you prove this? So, this just uses the elementary properties of the congruence relation. Okay. So, if it is empty, the intersection is empty, then there is nothing to prove. So, start with intersection being non-empty. Okay. Assume that this bracket m intersection bracket b, this is non-empty. So, that means there exists C such that C is congruent to A modulo m and C is congruent to B modulo m. Okay. So, then this immediately implies that A is congruent to B modulo m. Okay. So, this is the first observation. So, now if you take, so we will claim if you x is in, okay, inside this residue class A modulo m, then you can easily see that x is congruent to A modulo m. Okay. Now, since A is congruent to B modulo m and x is congruent to A modulo m, this will force that x is congruent to B modulo m. So, this is just obtained from transitivity and reflex symmetric. So, now this will imply that x is inside the class B m. And similarly, you can retrace if x is in class B m, so that will imply that x is congruent to B modulo m. Again, together with A congruent to B modulo m would imply that x is again in class A m. So, this proves if x is in this class A, only if x is in this class B modulo m. Okay. So, that proves that these two sets are same. Okay. So, that means you can see that if I take two residue classes, either it is equal or they are, their intersection is empty, they are completely disjoint. Okay. So, now what we can do, we can actually write Z as definitely union of all those residue classes, because we can simply take A is from Z itself. Okay. Now, if you think about it using that earlier lemma, okay, so this sets this bracket A m, either they are equal or the intersection is being empty. Okay. So, that will force us that, so you can actually take all possible these representatives. Okay. So, you take this Z, so you have defined this relation on this Z. Okay. So, that will actually partition Z into these subsets residue classes of A modulo m. Okay. So, now what you can do, you can actually look at all possible disjoint subsets. Okay, you can pick one representative from each subset, and then you can make this another what is called this sets of representatives. So, if you think about it, this complete system of residues, okay, that we have defined. So, this x1 etc. xm. So, this is the complete residue system modulo m. Na? So, that exactly does that representative job. Okay. So, a moment thought can tell you immediately that with that definition, this Z can be actually written as disjoint union of this xi bracket m, where I ranging from 1 to m. So, this is all disjoint. So, Z can be written as x1 m disjoint union etc. disjoint union xm. Okay. So, now we already seen that how the bracket am looks like. This just looks like a plus m z. So, in particularly you wrote z as x1 plus a z, sorry m z, disjoint union etc. disjoint union xm plus m z. Okay. So, that is what indeed we have proved. So, this complete system of residues motivated from getting these representatives of this partition of Z with respect to this congruence classes. Okay. So, this is the set of representatives we can choose to be the complete system of residues. Okay, so let us do some examples, then it will become more clear. Let us take m to be 4, okay, then it is clear that Z can be written as 4Z union 4Z plus 1 union 4Z plus 2 union 4Z plus 3. Okay. Similarly, we can also write Z as, for example, let us say 9 plus 4Z, okay, union 8 plus 4Z. So, union let us take 11 plus 4Z. Okay. So, this corresponds to 1, this corresponds to 0. So, this corresponds to, if you divide by 4, then it is 8, it is 3. Okay. So, only 2 we need. So, you can take it to be, for example, 14 plus 4Z. Okay. 3 times 4 is 12. So, this corresponds to 2. So, all these residue classes are covered. Okay. Basically, what I want to say, this is same as 1 plus 4Z and this is same as 4Z and this is same as 3 plus 4Z and this is same as 2 plus 4Z. Okay. So, basically we are changing only the representatives, the residue classes stays same. Okay. So, now from what we have done so before, so we are taking these residue classes and then we are adding them. Okay. To add them, it is enough to add some elements from them. Okay. For example, if you use this notation, we want to define what is called this residue class of A modulo m plus the residue class of B modulo m. So, this is we want to define. So, this is a set, this is a set. So, you want to define this addition between these two sets. Okay. So, the natural way to do it, so you have already as addition in integers. So, this addition should be kind of inherited from the addition that you have already from integers, or it should actually agree with the addition that you have already in the integers. So, if you are tempted to define this is equal to A plus B class m. Okay. And then if you think about it, this is actually well defined, because if you take another representative, so what is the meaning of well defined? So if you take another class A equal to class A dash, and then class B equal to class B dash, so then we should prove that this class AB is same as class A dash B dash. So which is true from the elementary properties of these congruences, because this tells that M divides A minus A dash, and then here M divides B minus B dash, then that would imply that M divides A plus B minus A dash plus B dash. Okay, so this is equivalent to this. So that is why the addition that we have defined before agrees with this addition. So recall that this class A is nothing but A plus MZ, and this class B is nothing but B plus MZ. So we defined addition between these two sets as A plus MZ plus B plus MZ is exactly equal to A plus B plus MZ. Okay, so this is something happening inside integers, but this is somewhat agrees with the addition that we want to define between these sets. Okay, so treating them as elements, and then we are defining. So this is something I already shown you before, like how to do this addition modulo M. Okay, so basically I am trying to convince you that if you use this congruence notation, again you get the same thing. Okay, so this is kind of actually revises the definition of these congruences. Either one can use this set notation, or one can use this A congruent to B notation. So both are equivalent. In both ways, you can see that all the arithmetic that you do modulo M coincides. Okay, so basically now just recall what we did with this arithmetic modulo M. So we partitioned Z into M subsets, okay, disjoint subsets, which is MZ disjoint union 1 plus MZ disjoint union etc. disjoint union M minus 1 plus MZ. So then what we did, we constructed this new set which we denoted by Z modulo MZ. So what is this? This is a subset of power set of Z, okay. So which consisting of these as elements, okay. Basically is all the residues, you take it, all the residue classes. So what it is, if you think about it, this is exactly MZ 1 plus MZ etc. M minus 1 plus MZ. So there are M elements in this set. Okay, the cardinality of Z modulo MZ is exactly M. So then we define addition here. So we defined addition on this Z modulo MZ. So which is a finite set. So how the addition is defined? You take A plus MZ, and then you define this addition, maybe put dot here, B plus MZ, okay, maybe I will call it addition modulo this M. So this is defined to be A plus B plus MZ. So this is how we are defining the addition. For example, in the congruence class notation, if you take this residue class A modulo M, then the addition is defined to be, you take this residue class A plus residue class B, then it is defined to be A plus B. Yeah. Okay. So this is how we have defined the addition. So now what we want to say with respect to this addition, this Z modulo MZ with respect to this addition forms a group. So this is indeed an abelian group. Okay. So later we will see this is indeed cyclic group. Okay, because this 1 plus MZ, so which is same as this class 1. So, this actually generates this Z modulo emission. So, I will leave it to check this forms abelian group. Okay. Basically, you have to prove that this addition is well defined, which is already we proved, because this addition is inherited from the addition on integers. So, it will satisfy associativity, commutativity for free. Then if you take this MZ, which is 0 plus MZ, so that is corresponding to this residue class 0 modulo M. So, that will be the identity element, and given any residue class, so let us call it AM. So, then the inverse of this will be exactly minus AM. Okay. So, for example, if you want to write it for this 0 to M minus 1. So, if you take A plus MZ, where A is coming from 0 to M minus 1, then the inverse of this will be just M minus A plus MZ. So, this will be the inverse in your group. Okay. So, now this proves the existence of identity and existence of inverse. The identity is being MZ. So, it proves existence of identity, and then associativity and commutativity comes for free. So, that will make this Z modulo MZ is a group. So, now you can see that this 1 plus MZ is indeed generates your group. Why it is the case? Because by adding it repeatedly, for example, if you add it twice, so then you get 2 MZ, and then if you add it enough time, you get all the elements of Z modulo MZ. If you add it 3 times, so then you can see that you get 3 MZ and so on. So, this actually gives you all the elements of MZ, Z modulo MZ, by repeatedly applying 1 plus MZ. So, once you reach, for example, M times, so then you will get M plus MZ, you get back what is called identity. Okay. So, it's basically a cyclic group generated by this element. So, with this exponential notation, if you call this is A, then this is A square and so on, A power M minus 1 and then A power M, which is identity. So, that is what we use. Okay. So, we are running out of time. So, I will stop with this. So, here we have this one very good example of cyclic group, and later we will prove that any finite cyclic group must be of this form. Okay, up to isomorphism. So, I will stop here. So, thank you.